Welcome back. We are ready to do part two here, and I'm going to start you off this part two of polymers by looking at this particular picture. And what you can see if you look close up is little bits of plastic waste. You can see little pieces here, a little bit of some kind of mesh kind of material. This thing kind of looks like a comb that's been a bit through the wringer, some things broken off, little piece of string there. This is actually a close-up of a piece of art which I'm going to zoom out for you progressively. So that's zoomed out one more step again, one more step, and one more step again. This is a piece of artwork that is made of 2.4 million pieces of plastic, all of which were retrieved from the Pacific Ocean. That number, 2.4 million, is equal to the number of pounds of plastic that enters the oceans each hour, which is a staggeringly large number when you think of how much plastic is continuously being put into the oceans. So much has gone into the oceans that it's starting to become a very serious threat to certainly wildlife that are in the oceans. What happens to most of the plastic garbage that ends up in the Pacific? It tends to not break down very quickly. If you dumped something like paper into the ocean, it would break down very rapidly and wouldn't create a long-term problem. But plastic, not so much. It'll build up. And in fact, what happens is natural ocean currents concentrate this plastic garbage into different zones. And there's the smaller western garbage patch in the Pacific Ocean. And then between Hawaii and California, we have this other one right here, which is called the Eastern Garbage Patch, or sometimes the Pacific Eastern Garbage Patch. And this has about 5.1 kilograms of plastic per square kilometer. And that extends, of course, a very huge area. And this is bad for all sorts of things that live in the water. You can see here things like, sea turtles can mistake these pieces of plastic for food and accidentally ingest them. You can see the albatross up above. They are known as well for accidentally eating bits of plastic that they think of as food. And you can see this very sad picture here of one of these birds that has died. And after it's decomposed away, you can see what was inside the stomach before it passed away. And so, huge amount of just random bits of plastic that it had consumed. And of course, this is probably the reason it didn't survive. I got another picture for you. This is, as you can see, it's a bunch of used drink bottles, plastic bottles. I'm going to zoom out. Zoom out one more time. This is an image made with 2 million plastic bottles, which is equal to the number used in the United States every 5 minutes. And this is another piece of art by Chris Jordan, which again does a really nice job of putting into perspective how much plastic waste we are generating. And this is single-use plastic waste. Another piece, this is another piece that he made. It has 60,000 plastic bags, which is the number used in the US every 5 seconds. And you could probably guess that number in Canada is probably 1/10 of that number. Although what you're starting to see is people move away from single-use plastic bags. I think it was within the last month or so, Sobeys has phased out plastic bags in their stores. So you either carry it out in your arms or you bring your own bags, reusable bags. This is another image, and this one is not actually a piece of art. This is the inside of a dollar store in the aftermath of Hurricane Katrina. And this was all new stuff before the hurricane flooded the place. It just shows you, though, the majority of what you're looking at in this picture is plastic material. And so you can see the amount. It just gives you a sense of the amount of plastic that we are purchasing just all the time when you go out to buy anything. So what about all this garbage? I mean, ideally when garbage is or plastic is used, It is then collected and recycled. There is maybe, you see some articles that come out talking about potential biodegradation of plastics, and hopefully this is something where we make some major strides in the future. This is just one interesting one I wanted to show you. This was a high school student from Waterloo back in 2008 who won the Canada-wide science fair by finding a microbe that can actually break down some plastics. And the reason this is interesting is the runner-up, the second place winner that year, was a student that was in this very class. They've also discovered nylon-eating bacteria. So what is true is that for years and years and years, nature has been producing all sorts of variations of different carbon-based compounds. And before long, some microbe evolves to use it as a food source. So it's probably inevitable that at some point, because we're putting so much plastic into the environment, something will evolve that's able to degrade it, use it as a food source. But that can take thousands or millions of years for something like that to occur naturally. So in terms of the different polymers that we are using for the most part, I'm going to talk about the top 5 that we use in terms of their abundance. The first one is polyethylene. So polyethylene is made by taking this compound, ethylene, and ethylene actually itself comes from ethane, which is CH3CH3, and this comes as a component of natural gas. When you get natural gas out of the ground, it's mainly methane, which is CH4, but it does contain some amount of ethane, which is removed, used to make ethylene, and then this is polymerized to make these very long chains where each of these corners is a carbon, and each carbon has 2 hydrogens. So this is polyethylene. Polyethylene is the most widely used plastic. More than 100 million metric tons are made each year. 100 million is the figure from 2017. It's about a third of all plastic production is polyethylene. It's used mainly to make plastic bags. It can be used to make bottles. It can be made for all sorts of materials. So if you see kind of a sheet of plastic that looks like this, chances are it's polyethylene that you're looking at. Polyethylene comes in sort of 2 main flavors, I would say. One is called high-density polyethylene and one's low-density polyethylene. High-density polyethylene is like a single strand that you see right there, a single chain that kind of wraps back on itself back and forth, and because it's a single strand, it very efficiently packs together, and you can make a very sort of solid, dense material. And so this is used for things like this, these sort of bottles you might find hand soap in or something like that. They're rigid, they're solid, but they're also quite flexible as well. So you could squeeze them and you could squeeze the contents out, but if you just left them on the counter, they would hold their shape. These particular ones are recyclable, and they have a recycling code of number 2. If you're wondering what all those code numbers meant in the recycling symbol, it's the type of plastic that's used in that particular material. Low-density polyethylene, on the other hand, rather than being a very long chain, it's a chain that has branches, kind of like the roots of a tree. Because of these branches, the material doesn't pack as tightly as the high-density polyethylene, so you get sort of a more less structurally rigid, looser, more flexible kind of material, which might be more useful for making things like plastic wraps or plastic sheets or things that are otherwise going to be more flexible. Also recyclable under the recycling code 4. Polypropylene is number 2. Polypropylene is similar in structure to polyethylene, except there's this extra CH3 group attached to the ethylene molecule. So propylene, and the propyl means that there's 3 carbons. can be polymerized to make this compound here on the right, which is polypropylene. Again, each corner is a carbon. Those are carbons, and they all have enough hydrogens that are not drawn in, such that all of these carbons must have a total of 4 bonds to them. So polypropylene is sort of similar to polyethylene, except it's quite a bit more rigid, quite a bit more tough, and quite a bit more durable as well. It's the number 2 produced plastic with 74 million metric tons produced. That was in 2016. It's somewhat flexible, but also kind of hard and durable. So you see this plastic chair here. I'm sure you've sat down in chairs similar to that. That's the material that's used in these kinds of chairs. It's used a lot in as well drainage pipes, other things like that. So it's a very, very common plastic too. This would probably be used less in a single-use item and more for applications where something more durable would be wanted. This is recyclable under recycling code 5, and the PP here means polypropylene. This is just a paper that I wanted to draw your attention to. This is published in the journal Science, which, if you remember way back to the start of the course, I said was sort of one of the top 2 journals in all of science. So Science is one of them. The other one that's probably equally as important is Nature. And the reason why I wanted to talk about this one in particular is because of this affiliation you see right at the bottom, which is us, and that is Dr. Amitabh Jha, who's an organic chemist in our department. So this paper came out, it was looking at laboratory plasticware, and these were by and large made of polypropylene, but they had basically a material on them called a slip agent, which is something that makes the plastic not stick to other pieces of plastic. And they were finding that they were messing up some results that were done in some biochemistry assays. And it was just, this paper was sort of published as a warning to people doing these biochemistry assays that you have to be very careful what sort of plastic you're using and what might be on the plastic that could interfere with those tests. So this is just maybe our first hint that when you have a piece of plastic, it's often not just strictly the plastic polymer material that you're dealing with. There can be other additives either in the plastic or on the surface of the plastic. And I guess you know this, if you have a piece of plastic that's colored, it must have some sort of dye that's in there to create that color. So it's not just the pure polymer that we're going to be dealing with. We'll talk a bit more about that in a bit. The number 3 most produced polymer today, about 40 million tons per year, is polyvinyl chloride, or PVC. And polyvinyl chloride starts with a monomer, which is vinyl chloride. It is then linked together to make these very long chains. And again, all of these corners are carbons. We have enough hydrogens, right, to make each carbon have a total of 4 bonds. Hydrogens only like to make 1 bond, and chlorines only like to make 1 bond as well. PVC is a very versatile material. You can put additives in it to make it either very soft or very tough. If you have very few additives, it's a very hard sort of durable material that is very often used in plumbing. And you can see this pipe here is made out of PVC. It's often sometimes just called vinyl, which is a short, I guess, version of polyvinyl chloride. And it's recyclable in some places under the recycling code 3. So I have a picture here of a house. This was a picture that a friend of mine actually was considering buying at one point. And the reason I'm showing this picture is just to give you an idea how widespread polyvinyl chloride is. And even then, it's still only the number 3 plastic that's used. So in this house, all of the siding is vinyl. You jumped ahead there by mistake. What you also see here are the shutters are probably vinyl. Most gutters are vinyl. Probably a lot of the drainage pipes inside of the house. You often see vinyl on decking. If it looks plastic, it's PVC. Plastic deck chairs are probably PVC as well. Um, so yeah, lots of vinyl, just visible. Vinyl is also a very popular material for flooring. If you have, yeah, you can get vinyl flooring as well. It's very popular. So just when you imagine how much construction material used to build something like a house is all made out of PVC. Here's two more things that are made out of PVC. We have a vinyl record, and we have this rubber ducky here on the right. Both of these are made out of the exact same plastic, which is PVC, and the two types of plastic here couldn't be more different in terms of their physical properties. The records on the left are hard, they're brittle, right? If you took a record and you accidentally dropped it on the ground, it would probably shatter. Whereas the rubber ducky is very soft, it's very pliable. You could throw that at the ground as hard as you could and it would just bounce. Nothing bad would happen to it. So how can these possibly be the same material? Well, what happens is, look, I have polystyrene here. That's not polystyrene, this is PVC. What happens is you take the plasticizers, usually a molecule called phthalates, and you can add them to that plastic while it's being made in any amount up to about 60% of the mass. And the more phthalate that you add, or the more plasticizer, the softer and less brittle it becomes. So this duck here has probably 50% or so plasticizer. Whereas these probably very low amount. So Barbie dolls, when they first came out in the 1960s, were a very big success. Barbies are made out of polyvinyl chloride as well, and they have a certain amount of plasticizer in them, which makes the plastic feel sort of soft. It's not hard and rigid. It's kind of more flexible. And you can see this picture on the right. You can see poor Barbie's ear looks very green all around it. And that's actually because the original Barbies, and you can see it in this picture, were sold with earrings on, and the earrings were made out of copper, or contained at least copper. And copper over time will oxidize to make copper oxide, which is sort of a bluish green. And these Barbies, which are big collector's items now, these original Barbies, if they're stored with the earrings in, they have this sort of bluish sheen around the ear, which is the copper oxide. And this is almost inevitable unless you store your Barbies with no oxygen or you take the earrings out. You're likely to have this problem. So if you have one of these Barbies with still have the earrings but without that bluish thing, I think they're worth a lot more. And you might be wondering why I know so much and about Barbie collections. I do not personally collect Barbies, so I can't tell you much more than that. These phthalates have a structure which looks more or less like this. And these phthalates are a huge class of chemicals. There's not just one structure. There's many, many different variations of phthalates. They're used in plastics and they're used in a lot of other things too. Some of them are very nice scents, so they're used in perfumes and things like that as well. And there's certainly been some concern expressed over the years about the safety of phthalates. And I believe there's been a lot of testing on a lot of different phthalates, and several of them have been banned for use in consumer products. So the ones that are currently in plastics that are being used are the less dangerous variations. One good thing about phthalates, at least, is they have very low acute toxicity and they have a very low residence time in our bodies. So if you consume these accidentally, they will very quickly, they have a half-life of maybe 1 or 2 hours in the human body. Very quickly break them down and get rid of them. The danger in these comes more from the fact that they're so ubiquitous in our environment. They're everywhere, and you can't really avoid them. And it's because they're used in plastic products all over the place. So while they may not be in and of themselves a particularly big threat if you get a dose all at once. It's more the cumulative effect that people are worried about over many, many years. So vinyl records, which are pure, or not pure, but more pure, they have less plasticizer in them than the rubber duck, but it's still the same material, still polyvinyl chloride. And one thing you might have noticed is that most vinyl records are black. And that color black isn't the natural color of the polyvinyl chloride itself. The actual pure plastic has no color at all. But all the records, sometimes you see some novelty records that are maybe different colors, but most of them are black. And this all stems from a 1961 patent, which I have here on the right, which looked at the conductivity of vinyl records, but with and without the color black added to it. And what's added to make it the color black is carbon. So it's just carbon black. Same kind of carbon, pure carbon that you might have remembered from our water purification chapters. So it's ground up into a very fine dust and added. And what's found is that by adding that carbon, it increases the conductivity of the plastic, because the PVC itself is a natural insulator, electrical insulator. And so what happens is if you didn't have the carbon in there and you started playing the record, what would happen is over time you would start to see a buildup of static electricity on the on the record itself. And when that static builds up, it tends to attract dust. That dust can settle into the grooves, and then when the needle moves through the grooves with the dust there, that would sort of grind the material and wear down the record a lot quicker. So they found that records lasted a lot longer if you add black carbon to the plastic during production, because it prevented that dust buildup, and they didn't wear out so quick anymore. All right, so one issue with PVC in particular is what happens if you actually burn PVC. So of course these toys here from Toy Story are probably largely made from PVC, and if you burn PVC, it can give off some pretty nasty stuff. You're probably told from a very young age that if you have a bonfire or a campfire that you don't burn plastic. This is especially true for PVC. And what happens with PVC is when you put it in fire and you try to burn it, it can create a type of compound called a dioxin. And dioxins are chemicals that have this basic structure. We have these rings where all of the corners are carbons, and these particular types of rings are called aromatic rings, connected by these two oxygens in the middle. And then they have some number of chlorines that are attached to these rings at various positions. So there's a huge family of these dioxins. Each one of them will have its own chemical characteristics, its own toxicity, and so on. But almost all of them are quite toxic to human beings. And this is a picture of Viktor Yushchenko, who was he was a former president of the Ukraine. He took office in 2005, and he was poisoned, likely by political foes, using some of these dioxins. And you can see he recovered. It didn't kill him, but it left his face very discolored. And this is a medical condition called chloracne, which is a product of poisoning of certain compounds that are chlorine containing. The worst of all the dioxins that we know of is this particular beast that you see right here, which is called 2, 3, 7, 8. So that refers to the positions 1, 2, 3, 4, 5. Wait a minute. My numbering doesn't work out, does it? 6, 7, 8. Maybe it goes 5, 6, 7, 8, 9, 10. That must be right. Anyway, this is the compound. This is the structure. It's abbreviated TCDD. It's believed to be the most toxic man-made compound. It has an LD50 of 1 microgram per kilogram of body weight, and this is measured in guinea pigs. This makes it about 1,000 times less toxic than botulism toxin, but much more toxic than any other human-made compound in existence. So this is one of the compounds that can be formed when PVC is heated to a very high temperature and burned. In addition to having a very high acute toxicity, as measured by its LD50, it's also classified as a Group 1 carcinogen by the IARC. And it has an ADI which is extremely low. Look how small this number is. 0.7 picograms. So PG stands for picograms. This means that you have this number, it's like 1/1,000,000th of a gram. You need less than that per day to remain safe. So it's extremely small. The other problem with this particular compound is it has a very long lifetime in the environment. It doesn't break down very readily at all, so if it gets into the environment, it tends to stick around for quite a long time. This is just a journal, Environmental Science and Technology, and it was published by people that I know that looked at the formation of these chlorinated dioxins following the collapse of the World Trade Centers in New York after the 9/11 attacks. And what they actually did was a few weeks after the towers collapsed is they wiped down the windows of stores with a solvent containing cloth, and then they put the cloth in a jar and then tested what was inside the jar for the presence of dioxins. And basically what they found was that the closer a particular building was to the site of 9/11, the higher the amounts of dioxins that were found. And they think this might be because as the building was burning, there was probably a lot of PVC inside that was undergoing combustion, which is creating these dioxins. In terms of any other hazards, some people worry too about vinyl shower curtains because they contain a volatile hazard. Volatile, of course, means that it can easily become a gas or enter the gas phase. And you might have known this if you buy a new vinyl shower curtain and you hang it on the first day. It has a very strong smell. If you're smelling it, those are volatile chemicals that you're smelling. So I guess maybe a suggestion would be if you buy a vinyl shower curtain is to do it on a day where you can keep the window open and air the place out a little bit. Or you could buy a shower curtain that is not made out of vinyl, like cloth or something like that. All right, we're going to take a break here and we're going to move eventually into part 3.